Hi, I'm Alex and I'm a H1 chemistry student. So today we're going to be doing a question on organic chemistry. This came up as question 6 this year, and it usually is as a question 6 that you'll see an organic chemistry question. So we'll fly into this and I'll go through all the important details of this question. So to start here, we're given two alkanes. We have on the left, which is octane, and then on the right, which is 2,2,4 trimethylpentane. So these will be the two that we'll be really using. They're called hydrocarbon A and B in this question. That's how they'll be referred to until we get on to the later question where we name them. So we'll fly in now to part A and part I, where they're asking us to describe a property of the hydrocarbons. So now part I, they're asking us to describe one property, so just the one, which hydrocarbon A has in common with other hydrocarbons in the naphtha fraction. So this is a question about fractional distillation and about your crude oil. And we know that at each level, they all come out, they all have a similar boiling point. So if hydrocarbon A is obtained in the same column as naphtha, we know they have similar boiling points. So for this, you'll receive 3 marks. They also accepted this year that it has a similar mass or size or a similar number of atoms as well. So any of those would have also given you 3 marks. And then part 2, they're asking us to state the systematic IUPAC names of compounds A and B. So A is octane and B is 2,2,4 trimethylpentane. I mentioned these a minute ago, but this is the names fully written out, so you know them. And I'll do a quick run through of how we got to this. I'll draw out the compounds and show you how they were named. But firstly, you got 3 marks for stating octane and then an additional 3 marks for 2,2,4 trimethylpentane. So let's go back here now to the exam paper and I'll show you how we achieved the names that we found. So we'll start with compound A, hydrocarbon A. And as we said, this is octane. So first thing with any of these, always just go through and count how long the longest carbon chain is. So if we start here with octane, we have 1, 2, 3, 4, 5, 6, 7, and 8. And then the next thing we'll have a look at is that they're all singly bonded and they are full of hydrogens, they're saturated. So we know that's an alkane. That's the general properties of alkanes. So we know this is octane since there's 8 members in the longest carbon chain. We'll do the same process now again for hydrocarbon B. So we'll go out and find our longest chain. So we have 1, 2, 3, 4, and 5. And that will tell us that this is a pentane. Again, it's all singly bonded carbons, so it's an alkane. But we also have 3 other groups on here. So we have this methyl group, and this one up here as well. So what we're going to do here is we're going to have a look at where they are in relation to the carbons. So what I mean by that is what carbon they're on. So we've numbered them 1, 2, 3, 4, 5. So we can see that there's 2 methyl groups on the number 2 carbon. So this fella here. And then there's only 1 on the number 4. So that's how we get our naming of 2, 2, 4. And then trimethyl, since there's 3 methyl groups, pentane, because it's a 5-member alkane. So that's how we achieved that naming. Then part 3 to this question, they're asking us to explain why compounds A and B are referred to as saturated alkanes. So I did mention this earlier, and since they only have carbon-carbon single bonds. So all the bonds are only single bonds, there's no double or triple bonds or anything like that. So that's how we know they're saturated. So for this, you'd receive 3 marks. And this year they also accepted that no addition reactions were possible and the maximum number of hydrogens were present. So either of those other answers would have given you the full 3 marks as well. We're back now at the main question. So we've part A done. So check that off. We've part I, and III done. And we got our total of 12 marks for that part. We'll fly on now to part B. And in part B of this question, they're going to ask us about the conversion from hydrocarbon A to hydrocarbon B. So we'll get into part I now of that. In part I, they're asking us to name the process that can convert compound A to compound B. So we're looking for the process here. So in organic chemistry, there's of course loads of processes that can be used to convert one compound to another compound or change them around a bit or add things on or remove things off. So based on the circumstances of this one, we know it's an isomerization. So that's 3 marks in this question. How do we know this is isomerization? Well, you could say that compound A and compound B are isomers of each other. So what does this mean? It means that they have the same chemical formula, but different structures. So there's the same amount of atoms of carbon and hydrogen present in A and B. They just have different structures from each other. So now part 2, they're asking us why is this conversion carried out? And that's to increase the octane number. And for that you would have received 3 marks. And this year they also accepted that it can reduce autoignition, smoother combustion, or increase branching. So any of those answers would have been accepted this year also. So we'll go on now to part C, which is all about the structure of the hydrocarbons. In the first part here, they're asking us to draw the molecular structure of methyl propane, including all atoms and bonds. So with the methyl propane, there's kind of 2 distinct parts here. So you have the methyl group and you have the propane. So we'll kind of break it down into its 2 parts and do it step by step. So with our propane to start, we know that propane has 3 carbons and they're all fully bonded, single bonded, and all have hydrogen surrounding them. So it's a fully saturated alkane. So we'll draw that out. So we have carbon 1 bonded singly to carbon 2 and bonded singly again to carbon 3. If we were to fill in all our hydrogens here, we'd fill in all around this carbon, all with hydrogens, and that would be our propane. But in this case, we don't have propane, we have a methyl group. And there's a reason why I left this space open on carbon number 2. And that's for our methyl group. So our CH3 goes on here. Again, it has all its hydrogens. But why does it have to go onto our second carbon? Well, if it went onto our first carbon or our third carbon, so on either end of the chain, we would just turn it into a butane. It wouldn't be a propane anymore, so it wouldn't be able to be a methyl propane as we're looking for in this case. So this is our full structure drawn out here now. And for this year, you would have received 3 marks. That's a really nice, easy 3 marks to pick up for a really quick drawing that you can just throw down on the piece of paper. So fly on now to part 2, and they're going to ask us to draw out some more structures of hydrocarbons. And in the second part of this question, they're asking us to state the systematic IUPAC names of 3 of the possible isomers of compound C. In each case, draw the molecular structure of the isomer, including all atoms and bonds. So there's a lot to go over in that question, but first of all, we'll find out what compound C is. In the question, it told us that a molecule of compound A, which we knew from earlier is octane, can undergo catalytic cracking to produce a molecule of methyl propane and a molecule of compound C. So we know that octane equals methyl propane and C. Because in catalytic cracking, you save all of the atoms. Nothing goes astray. Everything is just converted from one thing to 2 different products. So now to work out what compound C is, we need to look at the amount of atoms in each case and where they go. So the amount of carbons and the amount of hydrogens. So the atoms for octane, we know it's C8H18. I know this equals our methyl propane, which we worked out in the first part of this question, which we found was C4H10, and then plus our C. So how many atoms of carbon and how many atoms of hydrogen are in compound C? So it's literally just a small bit of work to work this out. So we know in octane we had 8 carbons, and then in methyl propane we had 4 carbons. So that means that in compound C there must be 4 carbons, because 4 plus 4 equals 8. Really simple maths, I know. And then we just do the same process with the hydrogen. So we had 18 to start with, methyl propane took 10, so then we have to have 8 remaining hydrogens in compound C. So now we have our chemical formula for compound C. So we can work out all of our isomers of this. So when I see this formula, C4H8, I think of alkenes straight away, since there's double the amount of hydrogens as there is carbons. So if you look at our general formula for alkenes, it's going to be CnH2n. And this follows that rule. So there's 4 carbons and double the amount, which is 8 hydrogens. So all of our resulting isomers are going to be alkenes. So what kind of alkenes can we get? So if we're going to start with our simplest alkene first, it's just going to be a straight carbon chain with no branching. So we'll draw out our 4 carbons. So C, 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 and C. So we have our 4 carbons, and since we know it's an alkene, there's going to have to be a double bond in there somewhere. So let's just stick it in the middle for this case. So after putting our double bond in the middle, we'll start filling in our hydrogens. So this carbon on the left needs to take 3, Since carbon always needs 4 bonds into it, we'll start filling in our hydrogens to satisfy all the carbons. So the one on the right hand side will be the same as well, 3 hydrogens onto that one. So we'll count the bonds going into the left middle carbon first. So we have 1 bond here, we have 2 here and 3 here. So that tells me we only need 1 hydrogen. It's going to be the exact same thing for the other carbon. So 1 hydrogen goes on here, and then we'll just do one final check. Counting around, we have 1 hydrogen, 2, 3, 4, 5, 6, 7, and 8. So we have our 8 hydrogens, and we know we have our 4 carbons. Since we have our structure drawn out and it satisfies our chemical formula, all we have to do now is name it. As we said, we have 4 carbons and it's an alkene. So straight away, you know it's going to be a butene of some sort since there's no branching. This is where it comes now to tricky ones with the alkenes where it comes to numbering. So we'll number our carbons. So it goes 1, 2, 3, 4. So since our double bond is on our second carbon, this is going to be but2ene. So we have but2ene as one of our isomers, and we have another 2 to find. So we're after finding our first isomer of our compound C. Now we're going to go on and try and find our second one. So what I've started it with here is the central carbons of our original isomer, the first one that we found, and just going to move things around a bit. So what happens if we move our double bond, say, from the second carbon to the first carbon? And then we'll do the exact same thing, fill in our hydrogens and see what we get. So on our first carbon, we fill in 2 hydrogens since it has a double bond, and now it has 4 bonds going into it, so it's satisfied. Our second carbon only needs 1 since it has a double bond and a single bond from carbons next to it. Our third carbon needs 2 hydrogens to get its 4 bonds, and then 3 hydrogens onto the final and 4th carbon. So now, when it comes to naming this, again, we know it's a butene, but which one is it? So counting from carbon 1 to 4, so if we go 1, 2, 3, 4, we can see that our double bond is on our first carbon, so this will be but1ene. So now to find our third isomer of compound C, instead of moving our double bond in this case, we're going to move one of our carbons. So if we move our 4th carbon in this case, move this fella away and throw it into the middle. So that's going to be a very different structure to anything we've seen before. And then again, we just fill in our hydrogens and then we name it. So throw on 2 H's here since it already has a double bond, and that satisfies its 4. This top carbon needs another 3. This carbon here needs another 3 as well. And then finally, the central one is already satisfied since it has 2 single bonds and a double bond to it already. Now to naming this. So first of all, we have to find our longest carbon chain. So if we go this way, start here, 1, 2, 3. And even if we go up, we can't find any shorter routes, including that double bond. It's important you include that double bond in your carbon chain. So we know this is going to be a propene. So we know this is a propene, but what's different about this than a standard propene? That's this top group up here. So all of this is different from our standard propene. But what is that? It's a CH3, which is also known as a metal group. So we just throw metal on the front of our name, and then that is our final isomer of compound C in this question. And then the marking for this question, so you received 2 marks each for each of the names, so a total of 6 marks for naming each of the isomers. And then you received an additional 9 marks, so 3 marks each for each of the structures. So that's a full 15 marks for this one question, and it didn't take a whole lot of time to get through. So now we've part C done, so we've CI and II done for a total of 18 marks there. We'll fly on now to part D. And part D is looking at the combustion of compound A. So we're given an equation and we have to work out the heat of combustion of compound A based on the information given in part I. In part I, we're told that the heat of formation of compound A is negative 250.3 kilojoules per mole. The heat of formation of carbon dioxide and water are respectively negative 393.5 kilojoules per mole and negative 285.8 kilojoules per mole. So you have to calculate now the heat of combustion of compound A. So there's a very much a step-by-step process to do this out, and I'll show you now step by step how we do this. So here's the equation that was given to us in the question for the combustion of compound A, also known as octane in this question. And we have to find out all the values to fill into this equation, and then we'll get our final answer for the full combustion of compound A. So to do it step by step, getting equations for each of the different compounds, and then add them all together at the end. So as we know, the formations were given, the heat of formations were given to us in the question. So that's where we'll start off. So now we're looking at the heat of formations of the following three. So the octane, which is compound A, carbon dioxide, and water. And how you work these out is on the left-hand side of the equation, you write out all the elements that make up these compounds in their ground state, or as they occur naturally in nature. So there will be a few funny ones pop up, and you'll see them as they pop up, but a lot of them will be quite easy. So now with octane, we'll have 8C plus, and then we have to count our hydrogens, and we know there's 3, and then there's 12 in the middle, and then our 3. So 3 and 3 is 6, and 12 is 18. So we say 18 hydrogens, but that's not how it occurs naturally. So instead, we have to write down 9H2. Since hydrogen is an exception, it occurs as H2 in nature. This is our full equation now for the heat of formation for octane, which is also known as compound A in this question. Let's do the same with carbon dioxide. So C plus, and we know the oxygen appears in nature as O2, so we'll just write down O2. Then the same with water, so we have H2, and in this case we only have one oxygen in water, so we have to do half an O2. I know it sounds a bit odd, but for the equation to balance and for it to be oxygen as it is in nature, we're going to have to write it down as half O2. So now, once you have all these equations written out, all you have to do is move them around until it looks like the equation on top, which is our heat of combustion for octane. So if we look at our first one here, number 1, which is the heat of formation of octane, we notice that octane is on the right-hand side, which we don't want. We want this to be on the left-hand side. So what I like to do with this is literally just draw a quick arrow like this over here and say that you have to turn this around. The next thing we're going to look at is that there's the right amount of octane there, which there is. There's only 1 mole in the above equation and 1 mole in our equation. So now we're sorted with this one. And now for equation 2, we're going to look at our carbon dioxide over here. That's the important one. And in the equation up here, we can see that it has 8. So all we do with this one is multiply it by 8. And then finally, with our last one, number 3, we look at our number of waters in our original equation, and we need to multiply this one times 9. So that's all we need to do now. We're going to flip our top one, multiply our second one by 8, and multiply our third one by 9. So now to work out our heats, all we have to do is see what we did on to the full equation and do that to our heat. So in equation 1, we said we flipped it. So instead of it being negative 250.3, it's going to be, in our case, positive 250.3 kilojoules per mole. And then with number 2, we multiplied it by 8, so write down the exact same heat, 393.5 times 8, and then it'll be the same thing for number 3. So negative 285.8 multiplied by 9. So now all we have to do is just calculate all of these and add them together. So from equation 1, 2, and 3, and then add them all together, and we'll get our final answer for the heat of combustion of octane. So now just throwing this into the calculator. So we have 250.3 kilojoules per mole plus, I'll do brackets here, negative 393.5 times 8, close the bracket, and then plus, bracket again, negative 285.8 times 9. I will calculate this, and we're given a final answer of negative 5,469.9 kilojoules per mole, and that's going to be the answer to this question. And now the marking for this question. So for writing down each of the equations, you received a total of 3 marks each. So 3, 3, 3. And then arriving at your final answer, you received an additional 2 marks. So that's a nice, easy 11 marks to pick up for something that's just, it doesn't change much every year. It's just step by step, and it's the same process. So it's something you can really learn the process of and fly through it then when it comes up on the exam. And now the final part, part 2. The question tells us that the heat of formation of compound B is negative 260.5 kilojoules per mole. Calculate the heat of reaction for the conversion of compound A to compound B. Okay, again, there's quite a lot in this question, but it's very simple. So all we're going to do is, we know our heat of formation of compound B, we know our heat of formation of compound A. We're going to get the heat formation of compound B minus compound A, and that'll give us our answer. It's really a simple process when you just break it down and just have a quick think about it before just diving in, not sure what you're going to do. So we're told that compound B is negative 260.5 minus compound A. We're going to just throw it in here, since compound A is negative 250.3 kilojoules per mole again. And this equals, all we do, throw it into the calculator, that'll be our answer. So now, just calculating this, negative 260.5 minus bracket minus 250.3, close the bracket, and we're given an answer of negative 10.2 kilojoules per mole. And then for working out this answer, you received an additional 3 marks, and then that's it. That's the end of this full question. So we can just tick off part D, I, and II, and we're through with this question, completely done. So it was a very kind of traditional organic chemistry question. So you had a bit of structure, you had a bit of calculations with the thermochemistry at the end, and they did a small bit about the explanation of isomerization and octane number and all that. But in general, really not a bad question at all. There's a few small bits, especially with the different structures and the isomers of each other. But once you just think them through, they really aren't that bad. So that's it from me. I hope this video was helpful.